Here's a kinematics question that you can find in Krotov's book called Aptitude Test Problems in Physics. And this particular question was given to students sitting the Physics Olympiad sometimes between the 1960s and the 1980s. And if you're not a student sitting the Physics Olympiad, this question might still be relevant to first year students doing physics or engineering as their degree. And if you want to see something similar in the future, or if you have any suggestions for topics or specific problems, maths or physics related, I'd be more than happy to read your comments. So let's see what this question wants from us. We have two rings called O and O prime, which are placed on two vertical stationary rods, which are called AB and A prime B prime. Now, those rods are somehow connected by a thread, but it's not that the rings themselves are connected by the thread. It's that the thread is fixed at point A prime, and then it's also fixed onto ring O. And then the thread passes through the O prime ring. And the question tells us that the ring, the ring on the right, the O prime ring, has a velocity um, that's directed downwards of value v1, and we also know the angle AOO prime, which is alpha. And we're asked to find the velocity of ring O, which is called, well, v2 in this case. So this is actually a constrained motion problem. And to do this, we're going to use this word in the question, which is this is going to be the key to actually cracking this. And we're going to use the length of the thread. And to do that, we're going to have to define a coordinate system. So the coordinate system of my choice is as follows. So any distance measured from the ceiling downwards is going to be considered positive. And I'm going to call that coordinate just y, okay? Which means that the coordinate of ring O prime, I'm going to call this y1, and the coordinate of ring O, this is going to be y2. So imagine this. Imagine that those arrows are fixed to the ceiling and the tip of the arrows are attached to the rings, right? And depending on how the rings move, the tips of the arrow move along. So they can get shorter or longer depending if the rings are moving up or down the rod. Okay, so for instance, we know that ring O prime is going down, which means that y1, the y1 arrow, the y1 coordinate, is going to get longer. Okay? So let's actually try to find an expression for the length of the thread. Okay, so I'm going to call the length of the thread capital L. And the thread is made of two parts. It's made of this y1 bit. Now it looks as if this first section here on the right is not perfectly straight, but because the ring itself is quite narrow, I'm going to assume that the length of this blue bit here is actually equal to y1. Okay, so I'm going to say that the length of the thread is equal to y1 plus, and then we've got this section right here, which we have to find an expression for. And let's try to see how we can do that. First of all, I'm going to say that the distance between the two rods is equal to small d, okay, lowercase d. And this is not going to change with respect to time. This is going to be fixed. So no matter what happens to those rings, the distance between the rods doesn't actually change in any way, right? So using this and using the coordinates as well as using this angle here, we can redraw this in a more familiar way. And this is what I mean. So this is what we're trying to find. And we know that this side of the triangle is D, and this is actually a right angled triangle, right? Because if we draw a line which is parallel to the ceiling here, like this, then you will end up with a 90-degree angle. And you know quite a few things about this triangle. So you know this side. You also know this side, which is y2 minus y1, right? And you also know this angle here, which is alpha. So that means that you can use those two sides to find the hypotenuse. So the hypotenuse is going to be just d squared plus y2 minus y1 squared. And that's just according to Pythagoras theorem, okay? And it turns out that this bit is actually the remaining part of the thread. So we can write the following thing. The total length of the thread is equal to y1 plus the length of the hypotenuse, which is the length of the thread from ring O prime all the way to ring O. And this gives us the total length of the thread. Now, how can we actually use this in any useful way? So the key here is that the thread is inextensible, so it doesn't actually get longer or shorter because it's always going to be taut. So if its length is always the same, that means that the first derivative of length with respect to time is going to be zero, right? Because if L is a constant, if you differentiate a constant, you get zero. So let's try to differentiate L, right? Because L is also equal to this, so I'm going to try and differentiate the right-hand side as well. So we're going to get 0 equals d by dt of y1 plus, and then we've got the square root of y2 minus y1 squared plus d squared. Okay, so what do we get if we differentiate each term? So if we differentiate y1, right? Remember that's the displacement of ring O prime. So if you differentiate the displacement, you're gonna get the velocity of ring O prime, right? So dy1 by dt is gonna give us v1 plus, and then we have to differentiate the square root, and we do that using the usual formula, which is this, and then of course we have to apply the chain rule. So I'm gonna make some square brackets, and now we have to differentiate what's inside that square root. So we have this, which is 2 times y2 minus y1, and we apply the chain rule again to differentiate what's inside the bracket. So if we differentiate y2, we get v2, right? Because y2 is the displacement of the second ring, and then we get minus v1, and that's it. Because if we differentiate d squared, we get 0 because d is a constant, right? So d is the distance between the two rods, which is a constant. You differentiate the constant, you get 0, and that's it. So now you can see that you can cancel out 2's. And what we'll get is that 0 equals v1 plus, and then we have y2 minus y1, and that's divided by the square root, which is y2 minus y1 squared plus d squared, and that times v2 minus v1. So we found an expression involving v2, which is really good, because it's v2 that we're trying to calculate. But this part of the equation, however, looks pretty daunting, because we don't know anything about the y's, we don't know what d is either. But it's fine because we can actually simplify this quite a bit. So if we go back to the triangle, this fraction is y2 minus y1. So in other words, it's this side, which I'll write here again. So y2 minus y1 over this square root. And if you look at this, the square root is actually the hypotenuse, right? So the hypotenuse is d squared plus y2 minus y1 squared, like that. And this is cosine of alpha, right? Because cosine is adjacent over hypotenuse, which is identically this. So this fraction is cosine of alpha, which really simplifies things because we know what alpha is. Well, we are told that we know alpha. So alpha is given to us. So if I rearrange this, I'm going to get 0 equals, and then I've got v1 plus. Now I'm going to replace the whole thing, this whole fraction by cosine alpha, but I'll write it like this. So V2 minus V1 cos alpha. So all we have to do now is just find an expression for V2. So we have 0 equals V1 plus V2 cosine alpha minus V1 cosine alpha. So V2 cos alpha will be equal to V1 cos alpha minus V1 by moving everything to the other side. So this will be V1 cos alpha minus 1, right? And if we take this and this, and if I differentiate by cosine alpha both sides, I'll get that V2 is equal to V1, and in the brackets we have 1 minus 1 over cosine alpha. Now you'll notice something interesting here, which is this term is a 1, and this is 1 over cosine. And 1 over cosine is something greater than 1 in this case, because in this case alpha is between, if you look here, somewhere between 0 and 90 degrees, right? So this quantity is actually negative. So I can rewrite that as V2 equals minus V1 times 1 over cos alpha minus 1. Now, why is this actually negative? What does this negative velocity actually tells us? Well, it tells us that our initial assumption regarding the derivative of y2 was not actually correct, but that's not a problem because we assumed both velocities. So we assumed everything going down to be positive, and we assumed V2 to be positive. But because we have this minus here, and this is clearly going to be a negative quantity, it simply means that velocity V1 is going up. Sorry, velocity V1 is going down, velocity V2 will be going up, and that is given to us by this minus sign here. Okay? And the reason why one velocity is going up and the other one goes down, if you want to think about it in a more qualitative manner, that is actually related to the fact that the length of the thread has to be constant. So if one ring goes down, the other one must go up with a velocity which satisfies this expression. And that's the end of the question.